The second causal inference design we're going to talk about in this unit is called a regression discontinuity design. And this is particularly helpful for establishing the effects of a program that has some kind of entrance level or cutoff requirement before you're admitted into the program. So difference in difference design is really helpful when we have some kind of treatment or intervention or a policy at a given time period and comparing before and after. This one is going to compare those who are in the program to those who are just outside the program. So let me start by talking about kind of the causal assumption that we're making here. So imagine that there was some kind of program that was intended to help people who were low income. And let's say that said that the cutoff for this program was $30,000 a year. So if you make less than $30,000 a year, you get this subsidy or benefit, or you're part of this program. And if you're over 30,000 a year, you don't. Well, causally, we think about the difference between someone who makes $30,001 and someone who makes 29,999. That's really just a difference of $2. And so we don't have any real reason to believe that the person who makes just over 30,000 and those who make just under 30,000 would be systematically different from each other. They're very similar. The only thing that really sets those two groups apart is the fact that one is admitted into this program and the other isn't. And that's kind of the causal assumption that we take with this method is we're going to look at a program with a specific cutoff, and we're going to look at everybody who's just on this side of the cutoff and everybody who's just on this side of the cutoff, kind of as a treatment and control group. And then we're going to assess whether there's a large systematic difference or a discontinuity. That's what the name of this design is called. If there's a discontinuity between those two groups, then we can attribute that to the cause of the program because they really aren't making that much difference in money. And so we would attribute any discontinuity that we see between those two groups to the program. So again, let's jump into a practice problem. It's a little bit easier once we get the data out and look at how we designed this kind of inference design, and then look at how we calculate that using regression.
Okay, the problem reads the city of Camorra Springs implemented a public transit subsidy program aimed at increasing the use of public transportation among low income individuals. The program offers free monthly transit passes to individuals with a monthly income below $2,000. The goal of the program is to encourage greater use of public transportation. You're provided with data for 50 individuals whose monthly income is just below and just above the $2,000 cutoff. Assess whether receiving the free transit pass has significantly increased the number of public transit rides taken per month. Okay, so we have the data here. So these are each of the 50 individuals, and we have what their monthly income is and the number of rides per month on average that they take. Before we jump into measuring the effect of being in this program, there's just one thing we want to check to make sure we can actually make causal claims about this program. So, one worry we might have is whether or not individuals are self selecting into the program by determining how much money they make. This is called bunching. So, the idea is that individuals might be intentionally not making more money month to month because they want to stay in the program. So it might be hard to think of it in this situation, but think about maybe for food stamps. Someone who is given food stamps, if they go and make more money, and if they fall just on the other side of the cutoff, then they will no longer have food stamps. And so they may intentionally withhold and not make additional money and make sure that they're just below the cutoff. And if that happens, then we get a bunching of a whole bunch of people who are just below the cutoff. And so then it's not really an accurate assessment. It's not randomly distributed across both sides of the cutoff. People are intentionally self selecting, and so our causal argument is no longer valid. And so we just want to check and make sure that this is okay. So the way that we would do that here is we're going to make a histogram that'll show each of the different incomes and how frequent those incomes are. We want to see if there's a big bunching of incomes right below the cutoff. So we'll start by let's figure out what our max and our min for incomes are here. So I'm going to start with the min. Okay, so the minimum is 1,800 and the max is, oops, try this again. Okay, the max is 2,200. So let's do this. Let's go from 1,800 and let's do $100 increments up to 200. And what this is going to do is it's going to tell Excel, I want you to count up how many are within these categories or bins. Okay, so this is going to be income, and then we want some kind of frequency. Okay, so the way that we do this is we go to data, data analysis, and then we select histogram. We select OK. So the input range is going to be our monthly incomes. Okay, and we've got labels selected there. And then the bin range is going to be our income here. So this is telling it, I want you to count the number of people who fall in each of these bins in between these groups. Okay. And then the output range, let's go ahead and have them put it right here. We'll select OK. Oops. Didn't like that because we've got multiple things here. Okay, so here we go. So we have our frequency here, and it also charted our output. Now, as we look at this, there is kind of a normal distribution, which is okay. We might be a little bit worried about this right here. It looks like there might be some bunching, but as we look at where this is at, which side of the cutoff is it? It's actually on the side of being out of the program. So looking at this, we wouldn't be worried that people are intentionally not making money so that they can stay in the program. If anything, they're just outside of the program. So for our causal argument, we're okay here. We like this. There's no bunching just on the inside of the cutoff. So this looks like a great normal distribution across that cutoff point. So the next step is we can actually just graph this, and let's just do an eye check. By eye check, I mean if we graph this, if there is a discontinuity, if there's a difference between being in the program or out of the program, then when we graph all of these data points, we should see a cut in the data right around the cutoff. Okay, so the way that we'll do this is we're going to just use a scatter plot. So we're going to select just the income and the rides per month. And we're just going to create a scatter plot of this. Insert, scatter. Okay, let's bring this back up by the rest of our data. So as we look at this, what do you notice? So right around the $2,000 cutoff, can you see this cut in between the two groups? So those who are just over 2,000 who don't qualify for the program, they're riding down here. And those who are just inside of the cutoff, they're over here. Now, again, causally, there's no reason why these individuals should be that different in the number of times that they ride. They make basically the same amount of money. But because this group qualifies for the program, we can see that there's this discontinuity here around the cutoff, and it's looking like this is definitely has an effect. So the last part here is we want to actually calculate the size of this effect. So it's great to know that there is an effect. More helpful is that we want to know being in the program is associated with how many additional rides per month. Okay, so in this one, we're also going to use regression analysis. But before then, we also need to create another dummy variable here. So the reason we need a dummy variable is the regression analysis won't be able to determine which of these are qualified or not. So we need a dummy variable that is qualified. And we want this we're going to use an if function. And if this is less than $2,000, so if they're less than the cutoff, the value of true is 1, value of false is 0. Okay, and we'll just drag that down. So now we have our dummy variable. So this is 1 if they're in the program, 0 if they are not. Okay, and so the last thing that we can do now that we have our dummy variables, let's run our regression. So we'll go to data analysis, and regression. And same thing. So the outcome variable is our y range variable. In this case, we're interested in rides per month. We want to know if it's leading to more additional rides each month. And for the X range, we're going to select qualified. So whether or not they're in the program, that's going to be our X range. We'll select labels there, and our output range. I'm going to make sure this is in the right spot. I want it to go right here. Okay. And we'll hit OK. All right, here is our output here. Now remember that the coefficient here for qualified tells us for a 1 unit change in the independent variable, how much does the y, the dependent variable, change? So think about what qualified is. Well, what's a 1 unit change in qualified? Well, it's going from 0, not being in the program, to 1, being in the program. So going from not being in the program to going into the program is associated with a 6.8 increase in the number in the dependent variable, which is rides per month. So being in the program, being part of this qualified group, resulted in a 6.8 increase. So now we actually have our size. And this actually tracks, right, with what we're looking at here. If you were to look at these two groups, if we were to guess an average for this group here, it'd probably be around 15. If you were to guess an average probably around here, it's probably around 22. So we can even see that like the average effect size is about 7. So that even tracks with the graph. And finally, this also produces a p-value for us, so we can know whether this difference is statistically significant. So again, in this case, this is a very, very, very small number, so the probability that this difference occurred just by chance is very low. Okay, so this is a regression discontinuity. So again, this is good anytime we have a program that has some kind of cutoff point, or if there's some kind of assessment of some people who are in and some people who are out, then we can look at people who are on both sides of that cutoff and make a causal claim about whether the program leads to better outcomes. Okay, we'll practice this more in class. We'll see you then.